Okay. Greetings, everyone. Give me a second here to get my desktop up for you, and we'll be underway. Okay.
Looks good.
As Jamison said, we're going to be talking about the use of at-risk and food safety risk assessment today. So what I'm going to do is give you just a real brief introduction of myself. I'm a professor of economics at Notre Dame, Maryland University, and I've had the opportunity to do a great many different kinds of risk assessments in a lot of areas. So what you should know is that I'm more of a subject matter expert in risk assessment and model building than I am in the food sciences. But all of your questions will be welcome nonetheless. What I would like to do is take a couple of minutes, because we probably all come from a lot of different backgrounds and have different interests in food safety. So I'd like to provide just a little context for what we're going to be doing this morning here. Foodborne illness, and I'm using the United States as an example, is a very serious problem. In our own country, 1 in 6 people will get sick every year, and that amounts to almost 50 million people a year. About 3,000 times every year, a person sits down to have a meal that they will end up dying from. So I think we could all agree that when it comes to public health issues, there are few that are as serious as foodborne illness around the world. Risk assessment has been used very rigorously in the last several years to try to address this problem. So let's begin with the simple definition of risk, if we can. And I'm going to give you a conceptual model here. If you look in the literature, you'll often see this equation that says risk equals probability times consequence. That's not literally how you calculate a risk, as you'll soon see when we take a look at our risk assessment model. What this really is a conceptual model. And here's what it's really telling us. If either of those two elements is missing, if probability is a 0, it doesn't matter how serious the consequences are, there's no risk. And conversely, no matter how big the probability, if there's no consequence, there's no risk. And I would grant you that that's rather trivial. So what we're going to do is take a look at how this has been translated a little bit for food safety. In food safety, we're using the same notion of a risk and the same 2 component parts, but they take on a different meaning, if you will. So we're going to be talking about exposure and hazard. Exposure is the likelihood that a human being becomes exposed to some sort of biological, chemical, or physical agent that could cause harm to a human being. And of course, hazard is that agent that can cause the harm. So as we move through this model, I'll point out from time to time where you're looking at these 2 different components of a risk model. What we're going to be doing with our example very briefly here is looking at a microbial risk assessment. If you were to allow me one word to answer your question, why do we do risk assessment in food safety or anywhere else for that matter, my answer would be uncertainty. One of the functions of risk assessment is to separate what we know from what we don't know. We want to get the good science in our assessments, and we want to be honest about the things that we don't know. And those things we don't know, that's the uncertainty. And for our discussion purposes today, I'm going to divide that uncertainty into 2 little piles. The first one is knowledge uncertainty. Sometimes there are facts in the world, and we just don't know them because we never collected the data, or just because we can't know everything. For example, if you don't know the capital of my home state of Maryland in the United States here, that would be a good example of knowledge uncertainty. It's Annapolis, and there would be lots of ways to reduce the uncertainty. And that's important to know. When we have knowledge uncertainty, when there are facts in the world and we don't have them, sometimes we can reduce that uncertainty by doing some additional work. Another component, another one of the piles of uncertain things, though, is natural variability. And this is just kind of capturing the randomness in the world, that we are dealing with very large food systems, very large natural systems in many cases, and there's just a lot of natural variability in the world. And that keeps us from knowing things with certainty. So as it turns out, if you're going to be doing risk assessment, qualitatively or quantitatively, probability is the language of uncertainty. And one of the things that you'll see as we move through this session this morning is at risk can help risk assessors to speak probability. Now, I want to introduce you briefly to this idea of Codex Alimentarius. This is the international food safety community. It is an organization that has been sanctioned by the World Health Organization and the Food Agricultural Organization of the United Nations, and it is basically where the nations of the world have come together to try to harmonize their views on food safety. I mention Codex because as we proceed through this demonstration, we're going to be using their definitions, their terminology. And part of that you need to know is this. Codex defines risk analysis as 3 tasks. First among these is risk management. So you see their risk management is policy-based. This is where values are important, and that includes politics, economics, environmental, legal values, and all those sorts of things. So value judgments are very much an important part of risk analysis. On the left, we have the second task, and the one that we'll be focusing on here today, and that's risk assessment. This is where we try to get the science-based information focused in our analysis. Notice that the Codex model shows assessment and risk management floating in this great sea of risk communication. And that's where the risk managers and the public and their stakeholders interactively exchange information and opinions about risks. Also understand that this is a classroom environment, and it doesn't always work out quite as nicely as the slides that we put up on the screen for you. But that would be risk analysis. Risk assessment, as I mentioned, is where we're going to be focusing today. So very briefly, if I define risk assessment informally, I would say if you are doing the work required to answer these 4 questions, you're doing risk assessment, whether you're doing it qualitatively or quantitatively. In food safety, we ask, what can go wrong? How can it happen? What are the consequences if this happens? And how likely are these consequences to occur? So they are basically the steps of risk assessment. Well, let's take a look at what Codex has to say about this. Codex formalizes those informal questions into 4 steps. First, they say you have to identify the hazard. What is that biological, chemical, or physical thing that can cause adverse health effects for humans? The second thing that is done in a risk assessment in food safety is then to characterize this hazard. Now that we've identified this thing, just what is it that it can do? What kind of harm can it do to humans? So this is where we would identify the health effects. And you'll see when we look at our model how these different steps are played out. Once you've identified what harm can be done, then the third step in the Codex model is an exposure assessment. And this is essentially where you describe how human beings come in contact with that hazard that you identified in the first step. These 3 steps involve a lot of science. They will also generally involve a lot of uncertainty as well. They all culminate in this 4th step called risk characterization. Now this, like the other steps, can be qualitative or quantitative. But this is basically where you estimate the probability and that consequence that you are addressing in your risk assessment. You would also do that by paying very close attention to the significant uncertainties that you encountered in this process. So that's kind of an overview of the Codex risk assessment model for food safety. We're going to be taking a look at a risk assessment for Vibrio, parahaemolyticus, in raw oysters. And this risk assessment, as well as the model that I will show you, are freely available to any of you from this FDA site. So let me show you briefly how to get a copy of this if you're interested in doing that. The first thing you want to do is to go to foodrisk.org. So you might jot that down if you're going to be interested in having a look at the model. And then you would go to the Risk Assessment repository. Once you click on this, you will see a great many different risk assessments available to you, and we're looking at microbial risk assessments. So you notice that Vibrio is highlighted at the bottom of your screen. So we're going to be looking at Vibrio, and we'll be interested in Vibrio seafood risk assessments. When you select these two items, it will bring you to a page like this with a number of Vibrio seafood risk assessments. And the one that we're using right here is from the Center for Food Safety and Applied Nutrition, Food and Drug Administration. I am not an employee of CFSAN or the FDA. I have over the years worked with a number of people and consulted briefly on some issues regarding this risk assessment. But in any event, this is how you will grab a hold of it if you would be interested in having a look at it. Very briefly, here is a schematic, a conceptual model of the risk assessment. This conceptual model is a little bit different from the assessment we're actually going to see, so we're not going to look at the details. I'll just ask you to look at the ovals that run down the center of the model here. Our model, as you're going to see in just a second, begins with water temperature. Water temperature is a major determinant in supporting Vibrio parahaemolyticus growth in the aquatic environment. And so we'll begin with water temperature, and then we're going to move on and see what our initial estimate of the total number of Vibrio parahaemolyticus per gram of oyster flesh is at the time of harvest. Moving down the center of our model, we're going to be doing some predictive microbiology in the model that's going to predict how the Vibrio in the oysters at harvest grows as the oysters rest on the deck of the workboat, and then how the Vibrio continue to grow once the oysters are put into refrigeration, because it'll take the oyster's flesh some time to cool down before the bacteria are affected. Once the pathogenic Vibrio are refrigerated, we experience some die-off then of the Vibrio. And so what we're basically doing is going to be looking at a model that estimates how many Vibrio are in a gram of oyster flesh at the time of harvest and how many are in the oyster flesh at the time they are consumed. Okay? So I have very ineloquently tried here to identify for you those parts of the model that are a piece of that exposure assessment. You can think of an exposure assessment as basically a story. This is the story of how Vibrio that begin in the water get into human beings. And the hazard characterization piece of our model appears down here. And this is basically going to tell us the likelihood of a person becoming ill. So now it's time for us to finally move on to the model. So let me switch on over to here and give you a view here of this model is the official FDA model for Vibrio parahaemolyticus in raw oysters. So let's just get oriented to the model first. Notice in the upper left, the indication here is that the data we're looking at are from the Gulf Coast of Louisiana. That's the southeastern part of the United States, and the data are from the summer. This risk assessment looked at many regions of the country and all 4 seasons. So we're going to be looking at just one small piece of this. In the center of your screen, you see a green column. This green column is basically where all the calculations get done, and I'm going to explain them to you and the use of that risk in them in just a few minutes. But what I would like you to understand right now is the green column is a model of one person on one eating occasion. So the language is a little unusual. You can think of an eating occasion as a meal. It's actually a bit more than that, though, because sometimes in the United States, we have something that we call oyster roasts, where people may show up maybe at noon and begin eating oysters at noon, and they would eat oysters throughout the day. So for this risk assessment, calling it a meal was not quite descriptive enough. So we're going to call this an eating occasion, but it's for one person and what they may eat over the course of a day. If you look at the lower right, you'll see three other columns that have three different colors. There's a beige, a light blue, and a purple. These three columns are basically showing us alternative risk management options, and I'll explain them to you in a few minutes as well. The yellow cells that you're looking at, we're basically going to be ignoring today. These are inputs to the dose response models and other kinds of details that we just won't have time to dig into. But let me walk you through this model here, the green column, if I may. This corresponds to what we were looking at before with the conceptual model. So let me just kind of point out some things without going into the details first. This model begins with one of the first important numerical inputs, and that is the temperature of the water in the Gulf Coast of Louisiana during the summer. Now, for the moment, just bear in mind that this temperature is going to vary. It's not going to be the same every day. So in this particular iteration of the model, for this one person that we're modeling, the temperature was about 28.7 degrees centigrade. There is an equation that was obtained from the literature that uses water temperature as an input to estimate the number of Vibrio in 1 gram of oyster flesh. This is in log count. So this is 10 squared Vibrio per gram of oyster flesh. And that's what's in the oyster at the time it's harvested. So what we're beginning to do now is to tell the exposure assessment story. This is how a person comes to be ill from Vibrio parahaemolyticus, eating raw oysters. So there's 2.4 log at the time of harvest. The next thing we needed to know was how long do the watermen stay on the water? How long are they out there with these oysters? And you can see for this particular occasion, it was about 8.7 hours. And of that time, how long did the oysters, on average, rest on the deck of the workboat unrefrigerated? And the answer here, for this one particular calculation I'm showing you, was just under 5 hours. And so now what we do is we take the air temperature. The details of this, don't worry yourself too much with the details if you don't understand perfectly. It's a complex model, and in the time available to us, we can't go through all of the details. But the air temperature is relative to the water temperature. So a negative number here is just saying the air temperature is cooler than the water. But using those temperatures, what we find is the air temperature is about 27 degrees, and at that temperature, the Vibrio are going to continue to grow. So once again, we have some equations in the model obtained from research and from the literature. If you look up here at the function bar, you'll see the equation goes on at some length. So we're not going to worry you with the details of it right now. But we had some estimated outgrowth. For those nearly 5 hours that the oysters sat on the deck of the boat, they increased by 0.2 log per hour, and that was almost 1 log increase. So at the time that the waterman first gets the oysters into refrigeration, there are now 3.4 log count of Vibrio for every gram of oyster flesh. Next, the model asks, how long did it take the oysters to cool down? And this will vary from one boat to the next because some have refrigeration units in their workboats, some use ice, some use a lot of ice. So this is also something that's going to vary from one workboat to the next. During those 5 hours of cool down, the Vibrio continued to grow, 0.6 log count worth, so that at the end of the cool down, there were almost 4 log of Vibrio for every gram of oyster flesh. Now, the oysters remain in refrigeration for some period of time. For this particular example that we're looking at, they were refrigerated for 7.7 days before they were consumed. During that time, there was some die-off. So we've been describing a lot of predictive microbiology here. That's one of the reasons that I've chosen a microbial risk assessment. They tend to be richer in detail than some of the chemical risk assessments, although chemical risk assessments can be complex as well. But notice at the end of cool down, there were almost 4 log per gram of oyster flesh, and now we're down to about 3.5 log per gram of oyster flesh. The next thing we need to know for this eating occasion is how much did this person eat? So this person ate 383 grams of oysters. I will show you when we begin to use at risk how the size of the meals can sometimes become very great, especially when people are eating over the better part of a half a day. Doing some simple multiplication, we can figure out how many total Vibrio parahaemolyticus were consumed in this one eating occasion. And you can see here that was a very large number. Now, not all of those Vibrio are harmful to humans. So we have to estimate of all of those Vibrio, how many cells were pathogenic Vibrio. Now this again, getting from the large number of Vibrio to the pathogenic Vibrio involved some science that is outside the realm of what we can address in our short time here together. But those data, that kind of information is what is gleaned from the literature. In this particular case, this person, this eater, consumed 2,929 cells. In log count, that's about 3.5 log counts. Now down here, this is saying if you consume 2,929 cells, your probability of becoming sick is about 1 in 10,000. So that's not a great probability. And most people who would consume this many pathogenic Vibrio, of course, will have no problems. But as you may suspect, the real issue is that many hundreds of thousands, or even millions of people are eating oysters. And if you had many thousands of people consuming 2,900 pathogenic Vibrio, we would begin to expect some unlucky souls among that group to become ill. But we also know that the number of Vibrio consumed in an individual meal is going to depend on all of those things that we've been talking about up to now. So down here at the very bottom, this is the punchline. If this is a 0, it means this person modeled in this green column did not get sick. If it's a 1, it means they did get sick. And very soon, we're going to be looking at how at-risk helps us to speak probability, and we're going to understand that. But here's one more thing that you need to know. Back up here in row 31, we had the number of Vibrio per gram of oyster flesh at the time cool down was complete. And so one of the things this risk assessment was doing was trying to find out how effective would heat treatment be in reducing the illnesses. So this beige column is basically saying, suppose we required by law or regulation that all oysters must be cooked. So that would be a 4 or 5 log reduction in the Vibrio. So this is basically saying, let's take that same oyster flesh with the 3.98 count, and they trace it down through this model, a different route, assuming that it's cooked. In a similar fashion, in this column over here, the light blue, this was investigating the effectiveness of a freeze treatment. Suppose there was a food safety regulation that said you must freeze all oysters. So it also took the same 3.9 and traced its fate, assuming a 2-log reduction through freezing. And there was a third risk mitigation measure that was used. And you can see it in the purple cell. And it's basically saying, suppose we had rapid cool mitigation. Suppose we passed a regulation that said, you've got to get those oysters cooled down within an hour of the time they're caught. So we're just going to look at one column, one row, just so you have some feel for what this risk assessment is doing. And then we're going to go in and look at the use of at-risk in particular. But notice in row 34, under existing conditions, there would be 3.48 log of Vibrio per gram of oyster flesh. If we have a heat treatment, that drops to -1. With the freeze treatment, the 3.5 drops to about 1.5. And with rapid cool, the 3.5 drops to about 2.5. So again, the details we're going to have to leave for your interest if they take you in that direction. What I would like to do right now, however, is to begin to walk through an explanation of how at-risk helps us to do this. Because here is something I would like you to see. Obviously, each meal is not going to be 2,929 Vibrio. I'm now going to turn on the Monte Carlo process for at-risk. And what that does is allows us to look at a number of what-if situations. Now, I will be explaining briefly in a minute what's changing and why this is happening and how this is happening. But what I would like you to see is we don't really know. One of the key uncertainties is how many pathogenic Vibrio is a person being exposed to when they eat oysters. Now here I've just stopped, just by dumb luck, on someone who's consuming 1 pathogenic Vibrio. Look up in row 36 at the size of the meal that this person consumed. This was 1,500 grams of oysters. I would think that would make you sick whether you had pathogenic Vibrio or not in it. But that's the point. There's a lot of variety out there. Some people will eat oysters all day long. You know, some people will eat a kilogram of oysters, and that's a lot of oysters. And some people will be exposed to a very large number. What I also would like you to notice is that we use that number of Vibrio in a dose-response curve, and that changes the probability. 10 to the -6, 10 to the -5, 10 to the -4, and so on. But the bottom line down here is what's important to us. And for the most part, every time I hit my recalculate button, you are seeing people who are consuming pathogenic Vibrio who are not getting sick. The risk of getting sick is actually quite small. The problem is, of course, a lot of people eat these. So let's go back up to the top now, and we'll take a look at some of these values here. So I was talking about uncertainty before, and I was talking about natural variability and knowledge uncertainty. In the Gulf Coast of Louisiana in the summertime, there is no uncertainty. There's no knowledge uncertainty about the mean water temperature. We know it. We also know the standard deviation. Those things are known with certainty. There are buoys in the Gulf Coast area that record the temperature hourly, and so we've got excellent data there. So even though these two values are known with certainty, we don't know on any given day what the temperature will be in the Gulf Coast of Louisiana in the summertime. So how do we convey that? Here you see a number with seemingly great precision in the decimal places. I've left the model as you would find it if you retrieve it. But what we see instead of a number when I click on the at-risk software to define distributions is actually a distribution in here. And this distribution has its mean 28.65 and a standard deviation of 1.32. So here's briefly what happens if you're new to the Monte Carlo process. Think of a number line that goes from minus infinity to plus infinity. What at-risk enables me to do is to say, I do know some things. Remember, risk assessment separates what we know from what we don't know. I do know the mean and the standard deviation of the water temperature, so I know that. What I don't know is what the temperature is going to be on any one given day. So with that risk, I can take that infinitely long number line and say, focus on the area, let's just look at what's on our screen here, from 25 to 32 degrees centigrade. The temperature is going to be somewhere in there. Now imagine that I could have a conversation with my computer, and I'm telling it, it's somewhere between 25 and 32 degrees. And the computer might say, fine, can you tell me anything else? And let me see, I'm trying to bring up my cursor here. I hope you can see. I would say I could imagine, and we'll forget all the math for the moment, just imagine I could take a pen and draw this blue curve here, this normal distribution, and say, yes, when I hit F9, I want you to pick a number from this number line at random. But I'd like you to follow this rule, the rule of this blue shape that we're looking at, so that most of the values are going to come from the fat part of the curve. So that means more often than not, I'll see numbers between 28 and 29.5 or so, say 28 to 30 degrees. That'll come up most often. And every once in a while, I would have values in 26, 25, when those days when the water was unusually cold, or days when the water's unusually hot. But those values are going to be unusual. So think of these probability distributions as pictures of what we expect or believe to be true. Now, that's not a very rigorous or even a very fair explanation to give you, but we only have about an hour, so I want to give you some intuitive feel. And those of you with quantitative backgrounds can appreciate better what's really going on here. So I'm going to say, okay, and we'll close that. And now just focus on this water temperature. So at-risk enables me to characterize the range of water temperatures in the Gulf Coast of Louisiana in the summer. And you can see as that changes, so does the starting amount of oysters, starting amount of Vibrio parahaemolyticus in the oyster flesh. So let me pull up my comment one more time now so you can have a look at it. This distribution here, this is an example of natural variability. There's absolutely no uncertainty about the mean or the standard deviation. Those parameters are known with certainty. But those parameters also define the natural variability in this Gulf Coast summer aquatic environment. And so at-risk enables us then to speak this probability and enables us to deal with the uncertainty in our risk assessments in a realistic way. Now, I want to make sure there's time for questions, so don't panic. I'm not going to go through such a detailed explanation of every number, but I do want to do one more here. One of the questions was, how much time do the watermen spend on the water? And it turns out that when we were doing this risk assessment, we didn't have a very good idea about what watermen did. The microbiologist knew a good bit about the predictive microbiology, about how Vibrio grow and die and those sorts of things, but we didn't know a lot about how watermen, the people who harvest these oysters, went about their business. So with not a great deal of quality research, but with a telephone, we were able to call some people and find out that the watermen said that the minimum time on the water, look at row 13 if you like, they said, we're not going to spend less than 5 hours on the water. If we go out, we've got to spend some time out there. They said, we can't spend more than 11 hours because we have to be back in time to get the oysters to market. So think of that long number line again that I was talking about, that infinitely long number line. I have now zeroed in to 5 and 11 hours. So once again, imagine me having a conversation with the computer. The nice thing is at-risk enables that conversation by allowing me to draw these rules. You think of the computer saying, okay, it's somewhere between 5 and 11. Do you know anything else? And I do. From my telephone call, I know that 9 hours is the most likely. So what happens is at-risk enables me to grab 9 and to lift that number up, and that makes it special. But I really only have 3 pieces of information here. We wouldn't necessarily call this data. You know, if I surveyed, 1,000 watermen, then I'd have some data. Right now, what I have is some information and my beliefs. And I have basically 3 points, 5, 9, and 11. At-risk gives me many options, or several options, for connecting those 3 points. At the moment, I've chosen a PERT distribution. Now, again, because of the limits of our time, I'm not going to spend much time talking about distributions, but this is basically using a spline, a curve, to connect my 3 dots. And once again, as with the other distribution, you can see every time I hit the recalculate, I get a waterman who spent a different amount of time on the water. And this determines this, together with how many Vibrio are in the flesh from the start, determine what happens before it gets to consumption. Okay, so I want to move down now, skip through some of these distributions, and I'm going to come on down here one more time. Let me scroll down so you can see a little better. We're going to focus on the number of pathogenic Vibrio here. Because the water temperature differs, and because the time spent on the water differs, and the time spent before refrigerating differs, and all those variables in blue, because they're all differing, every eating occasion has a consumer consuming a different number of Vibrio. Okay, so I'm going to stop here with about a person eating 21,000 pathogenic Vibrio. Down here, our last cell is rather important, and this is another instance where at-risk makes the modeling very nice, very convenient for us. I'm going to take a look at the distribution in here. Whoops, excuse me. Here we go. This brings up a binomial distribution. If you're going to be doing risk assessment, you're going to at some point have to learn this binomial distribution, in case you don't know it. Think of it this way. We've got one person. So over here, and I'm not really trying to teach anything about at-risk as much as to demonstrate its use, but over here on the left-hand side of this depiction of our distribution, we have parameters for the binomial distribution. N of 1 basically means this is one person, excuse me, eating oysters, raw oysters. And the p-value is found in E42. That's that probability of illness, 0.0007. So basically 7 in 10,000 people would get sick. The blue bars that you're showing, that you're seeing, are basically showing us a picture of what could happen. 0 is the person does not get sick. 1 is they do get sick. And I don't know how clear the resolution is on your screen, but there's a little tiny blue dot there that basically says, yes, there's some probability that a person will get sick. But what at-risk is going to do for us then is think of it this way again, and not a rigorous explanation, but one that's more intuitive. We're going to say to the computer, we've gotten down to 21,000 people. Using the dose-response curve, the science that we've gathered from the literature, we know there's 7 chances in 10,000 this person will get sick. So think of them piling 7 marbles over on the 1 and 9,993 marbles on the 0. And we say to the computer, reach into that bag and pull out a marble. You're going to pull out a 0 or a 1. And most of the time it'll be a 0. But if we do it enough, it'll pull out some 1s. And now what I want to do is show you how at-risk enables us to estimate the seriousness of this problem. So hopefully what you've seen up until now is that at-risk is a great tool that enables us to address the uncertainty that arises in the predictive microbiology for this particular risk assessment. So I'm going to put my cursor here in this cell. I'm going to do 100,000 iterations. So as I start the simulation here, what you're going to see in a second is at-risk is going to simulate 100,000 eating occasions for us. And it's begun to do that. Once it reads all the input variables, it goes rather quickly. You can look to the left and see the progress of our simulation here. And now what we want to do is find out what just happened. Because I can hit the recalculate button repeatedly, and I'll get a 0 or a 1, and I could record each one. That would take a long time. In the time that we just looked, less than a minute, I suppose, at-risk did a simulation of 100,000 eating occasions. And if you look over here, this is the result. The minimum value was a 0. That's when people are not sick. And the maximum that occurred was a 1. So that means some people did get sick. If you take 100,000 values, a mix of 0s and 1s, add them all up, and divide by 100,000, you get the mean, which you're looking at there, 0.00126. 0.00126 times 100,000 will give us back the number of people who got sick. So in this particular simulation, 126 people out of 100,000 eaters would get sick. Now remember, this is just one location in the United States and one season a year, but we're going to go with that for the moment. So we had one person getting sick, 126 people getting sick. Part of the risk manager's job will be to figure out, is that a risk that we can tolerate? Given the enjoyment people get out of raw oysters and the severity of their illness, can we tolerate that? And that's a question not for risk, or not for at-risk, but for those managers. But notice, at-risk lets me check now what would the results be if we had a heat treatment. And here, take a look, and it says the minimum and the maximum were 0. That's telling me if you cook the oysters, we can eliminate this problem. So that's good to know for a risk manager, but you're going to make a lot of people upset because people enjoy their raw oysters. So let's move over to the next column, and here we see the mean is 2 times 10 to the minus 5th. That means if we froze the oysters, we could reduce the illnesses from 126 people to 2 people. But again, frozen oysters are not going to make people happy because they're a little bit tougher than fresh. And finally, we look at the rapid cool. And we see the rapid cool, if I look at the mean up here, this reduced the number of illnesses from 126 to 15. Now let me jump back and we'll finish up a look at this and go to your questions. We've taken a look at the model, and what I would like you to know is when the FDA did this, you'll notice this is a table from their risk assessment results. The rows are different parts of the United States. The columns are different times of the year. And what you're looking at here is the expected risk for a serving of oysters. And the serving is actually that eating occasion. So let's just look at the total column over here, and we'll see that out of 10,000 people who eat Gulf Coast oysters, about 7 of them would get sick, okay? If we go down to the Mid-Atlantic and we take a look at 10,000 oyster eaters, there's about 1 who will get sick. So there are different probabilities of illness depending on where the oysters come from and the time of year that you eat them. And this enables risk managers then to make decisions regionally and seasonally. If we take a look at the actual number of people, that might be easier to work with, because once we get these rates of illness, we have to multiply them by the number of eaters. And so for the interest of time, once again, notice rows are regions of the United States, columns are times of the year. And if we look at the far right column total, most of the illnesses are coming from oysters harvested in the Gulf Coast region around Louisiana. We have about 2,826 illnesses a year. And again, this is an expected value. Once you see tables like this, it's very easy to believe this is good hard science. It's not. There's a lot of uncertainty in there. And we wouldn't have arrived at these numbers without a tool like at risk. So let me stop there because I'm afraid I've gone a little long, and I want to make sure that we have some time for you to answer, or excuse me, to ask questions. I seem to have lost my
Charlie, that was really great. That was that was an excellent application of our software, and I learned a number of things, that the way it was set up and the way you went through it, and I hope that helped a lot of people. I guess at first I was frightened by what I was going to find out, and now I'm still a little scared, but I understand things better, and I always want to cook everything, so.
Well, maybe I should give you the punchline. What they did do is they decided against cooking and freezing because there would be too much hue and cry among people who love their fresh oysters. They decided against requiring rapid cool because the waterman basically said it'll run us out of business if we all have to put refrigerator units. And what they ended up doing was regulating the time, the season. So that old, if you're from the U.S. region, we have a rule that says don't eat oysters unless the month has an R in it. And it turns out all the hot months have no R's, and so they're basically saying when the water's hot, that's when the Vibrio are most numerous. So that folk wisdom has some science behind it, I suppose.
Yes. Well, this was great. I think we do have a couple questions. There's one question that came in on the question panel, but I can't see that. Maybe
should I be able to see that, Jameson?
I think you might be able to see that.
Can you tell me how to go back? How do I go back to that view?
Let's see. Up in your top, you might have a panel, or maybe what I'll do. I think what I'll do this.
Should I hit stop sharing?
I'll take the. Let's see if I can see it. Ah, good. I've got it.
Okay. Yeah. Okay.
I've got it. How do you determine which distribution to use?
Jane, that's a great question, and that's probably the $100,000 question. And actually, I'll try to give you a brief answer, and I'll maybe even plug my book. I have a Principles of Risk Analysis book that spends a chapter on this because it doesn't get much attention. That's one of the areas that people are most likely to go wrong in. So there are a couple of things. The first thing I would say is if you've got extensive data, you don't even have to choose a distribution. You can just use your data. So for example, the water temperature, we wouldn't have to call that normal. We could just use our data. And at-risk has several tools that enable you to just use the data that you have. So sometimes the world doesn't fit neatly into a distribution, and my advice is always, if you've got good extensive data, first consider if you can just use your data without calling it a specific distribution. Unfortunately, we don't often have that kind of data that we can do that. So then there's a series of little steps that you go through, and I'll just kind of try to hit the highlights of them. The first thing you need to know is, is the variable that I'm trying to model discrete or continuous? For example, temperature, let's go with that. That's continuous. So I automatically can eliminate all the discrete distributions. Then you might want to ask, is this variable bounded? Does it have a maximum and minimum? And in a sense, I guess we could say temperature, maybe it is in some science fiction sense, but it certainly is bounded, even if we don't know what the bounds are. in the Gulf Coast of Louisiana during the summer. So once I decide it's bounded, now I'm looking at continuous distributions that are bounded. And so there are a series of sequences that you can go through like that. One important thing, now I'm jumping, I have about 13 such things I think I've identified in that chapter in my book, but one of them that's real important to me is theory. Sometimes we have very rigorous theory, like in statistics we have a central limit theorem. Other times we have less rigorous theory. But if you are a microbiologist, or if you are, if you are, I don't know what kind of scientist would know about water temperatures and marine environments. That's escaped me at the moment. But, you may well have some good theory that says, in this part of the world, you're more likely to have high temperatures than low. There might be a reason why there's a skew to the temperature. So you use the theory. One of the other things, once you've gone through all of the kind of step-by-step things you can do, and there are things, and I apologize that I can't do that more thoroughly for you with the time that we have, Stan. But once you've gone through that, then At Risk also has a very neat little feature where you can use goodness of fit tests. Now, where I would differ with some people is, they want to grab their data and go right to goodness of fit, and I'd say that's the worst way in the world. Once you've kind of narrowed it down, once you've said, okay, my data are continuous and they're bounded, and even though they're bounded, though, I think I can, use a normal distribution to approximate those bounds. And I might talk myself, as I go through each step, I'm looking at different distributions, and I come up with the normal at the end. At that point, I would use my data and some of the features of at-risk that we didn't explore that would test statistically whether it is likely that my data came from a normal distribution or not. So there's a good many different things that you can do to do that. I apologize that you got a skimming the surface kind of answer.
I think that may have answered the second question, too, about how much data is enough.
There's never enough data. We always would like to have more data. When I was showing you before the water temperature, that literally comes from tens of thousands of data points.
Oh, my.
So clearly, getting more data points there, it's not going to make much difference. It'll be out in the decimal, to the 4th or 5th place of a decimal. So sometimes you get lucky and you have enough. Other times, you're dealing with situations, like how much time do watermen spend on the water? Well, it would be great to have tens of thousands of data points there, too. But what we did was we're saying, all right, we got two problems here. This is a knowledge uncertainty problem. There is a fact. There is some average amount of time that watermen spend on the water. We just don't know what it is. And so you saw there the solution was pick up the phone and you call someone. So we got 3 data points. But the key is you got to be honest about that when you describe your risk assessment, too. You got to say, we're guessing here. One risk assessment I worked on some years ago with the Department of Agriculture, we were trying to estimate how many spores survived the digestive tract of a pig from a wheat bun. And I don't want to bore you with stories, but we basically didn't know. We had one data point, and so we built the uniform distribution. We said, it's no less than 30%, no more than 70. This was an important trade risk assessment with the Chinese, and so but we were very honest. We basically said, look, with that value right there, we are guessing. This is the only data point we have. If you have something better, please provide it. We'd be happy to use it. So, you'd like to have as much data as you can, but that's the thing, that with risk assessment, what makes it different from other decision-making paradigms is it says there are things we don't know. And rather than hiding that from decision makers, we're going to be open about that. So, in years gone by, if you didn't know something and you were the expert, you kind of, sweep that under the carpet because you don't want people knowing that there are things you don't know. But risk assessment saying, no, let's shine a light on it. So the choice of our distribution often conveys our level of confidence. When you see a uniform distribution or a triangle or a PERT, like I showed you in our brief demo, that's basically saying we don't have a lot of data here. This is our belief. This is what I believe to be true.
Good.
I
think we have a couple more time for one or two more questions. I have one it's interesting. It's about since you use the binomial distribution in the outcome, is there a way to model a distribution that encompasses the severity of the disease, or would you just say is that beyond the case of the study?
That's a great question, and when I do a lot of training in risk assessment, and I've had the opportunity to do a lot in food safety around the world. And if you get my full spiel, the very first thing I would have been telling you is you got to get the questions right. It's the risk manager's job. You know, if they're going to have to deal with this problem of Vibrio, parahaemolyticus, and raw oysters, they need to know what information you have to answer this question, to make decisions here about whether to regulate this or not, or how to do that. So if you don't think to ask, if your question is how many people get sick, then that's the model I'll build. And after I build that model, if you say how sick do they get, then I'm going to say, whoa, we screwed up here because I can't answer that with my model. No. So one of the things that is critical, even before you start building these risk assessments, is to sit down with the risk managers and make sure that you've got the questions that they want right. That risk characterization step, the fourth step in the Codex risk assessment model. How do we want to characterize this? Because if you want to know how many people die, how many go to the hospital, and how many stay sick for more than a week, that's a different model than the one you just looked at. So it's an excellent question, and actually it can't be answered from the model that we just gave you. We would have to go collect different data and restructure a new model.
I guess one more question. Would you be willing to share the model?
Well, that's if you recall at the very beginning, I showed you how to get it from foodrisk.org. So this model this is a public access model. This is available to anyone. So when you go to foodrisk.org, go to the risk assessment repository. Let's see, are we still on a share here? No.
Oh, sure. Let me give it right back to you. It's coming. Excellent. Here it comes. You've got the presenter ball. There we are.
Okay, so you go to foodrisk.org, Risk Assessment Repository. This is to gain access to risk assessments from all over the world, so it's a neat tool on its own. Once you get in there, you pick your hazard. We've got microbial here, bacteria, and Vibrio. Pick a commodity, and I'm looking specifically at seafood. And then if you hit go, you'll get this list. Look at the third one, Sipsan. If you click on that link, it takes you to here. And this is a little screen capture, but if I were to scroll all the way down to the bottom of it, the model that we just used is there for you. Matter of fact, there are two models. One has all the, there's one model just with some data. The data that were used to generate parameters for that model. You didn't see that today in what we did. And the second model would be the risk assessment itself. So that was the reason I picked this one in particular, because it's one that everybody can get. And if you like, this page also gives you the explanations behind the formulas and all the questions that you may have that we just didn't have time for.
Oh, great. Well, we really appreciate this.
I appreciate the opportunity. Thank you.
And what I'll do, everybody that's with us and those in the future who may be watching this recording, is it all right if they reach out to you, Charlie? And they might have.
Sure.
And what I'll do too is have I'll send a recording link out to everybody. And I suppose we should let you go. And very much appreciate this. This was great.
Yeah, thank you all, and take care.
Yes, you too.
All right, bye.
And thank you, everybody. Yep, thank you.